Now we're going to try out this example. What we're going to do is find the area of the triangle with the vertices located in 3 dimensions at 2, -3, 4, -1, -2, 2, and 3, 1, -3. Now, the way that we're going to do so is by using the area of a triangle formula that we derived in a previous video, which will be 1/2 of the magnitude of the cross product of 2 vectors that will help define this triangle. Now, in their current form, these are all points, not vectors. So what we're going to do is label these as 3 points, and we're going to turn them into vectors. So what we'll do is we'll use P for the initial point, and we'll use Q and R for 2 different terminal points to create these 2 vectors. So for the vector U, I'm going to join initial point P to terminal point Q. The way that we do so is by doing terminal minus initial. So -1 minus 2, -2 minus -3, and 2 minus 4. Simplify each of these, we'll get -3, +1, -2 for our vector PQ. For the second vector, we'll do the same thing. We'll use initial point P. This time we'll use terminal point R. So once again, terminal minus initial. For the first coordinate, 3 minus 2. Second coordinate, 1 minus -3. And for the third coordinate, -3 minus 4. Simplifying each of these gives us 1, 4, and -7. I'm going to take the cross product of these 2 vectors and then find the magnitude, take half of that, and that'll be the area of our triangle. So for our cross product, U cross V, this will be equal to, across the top we'll put ijk. Second row, we'll do -3, 1, -2. And it really doesn't matter which order we do this cross product in. I realize that we said that the cross product is anti-commutative, but once we take a magnitude, it's going to wind up being a positive number anyway, so no big deal. Once again, we'll recopy the first 2 columns. Gonna give you a little slashy. Hope you don't mind. So slashes in the downward direction, we account for these with a positive. -7 times 1 for the I component. -2 times 1 for the j component, and -3 times 4 for the k component. I'm sensing a lot of negativity right now. For the upward slashes, we account for these with a minus sign. We have 1 times 1 for the k component, so 1k. 4 times -2 for the I component, that'll be -8i. -7 times -3 for the j component, that'll be +21j. Then it's simply a matter of combining all of the like terms that we have. So that's -7 minus -8 for the I component. That'll be 1. For the j component, -2 minus 21. That'll be -23. And for the k component, we have -12 minus 1. That'll be -13. We need the magnitude of this vector, and if you're interested in verifying that this is the correct cross product, what you can do is dot this with each of these 2 vectors and verify that you get 0 for the dot product. The magnitude of this cross product is going to be equal to the square root of 1 squared plus -23 squared plus -13 squared. And as much as I feel like showing off today, I'm actually going to toss this into the calculator. I feel confident about the 1 squared, so we'll go ahead and leave that as is. So that'll be 699. I know that 699 factors into 3 times 233, both of which are prime. I think 233 is prime. So the area of our triangle is going to be half of this. So square root of 699 over 2, that'll be our final answer for the area. Now, there is a little bit of a corollary that we get here, which is when we calculated the area, we were able to get this non-trivial cross product here. Now, in the event that we wind up getting the 0 vector here, that means that both of the vectors would have been parallel to each other. So if you calculate the area and you wind up getting 0 for the area, the points are collinear. Boy, I hope I spelled that correctly. Collinear as in they all are on the same line. So imagine I tried to find the area of a triangle with 3 points that are all on the same line. You would essentially be taking 1/2 of the length of the base times a height of 0. So given that the height is 0, the area would have been 0 as well.